Hi everyone, and welcome to the second round of becoming a Filecoin solo storage provider. My name is Benjamin and I'm the VP of R&D at Picnic & Company, which is a Web3 storage provider in North America. So this video is intended for people who are considering to becoming a storage provider on the Filecoin network, but it could also be for current storage providers who are looking for optimizations to the hardware, or it could be for current storage providers who are looking for transitioning into storing actual data. So this video is not intended as an investment advice, and we are obviously still mining and talking a bit about that. But as we move into storing real data, that is the main purpose here, whereas mining in itself is more like what we're using to make sure that we can control incentives, and also for the basically the vehicle for transferring funds. But it's not the main purpose of what we're going to talk about today. So this will be a point of view on some different hardware that I've been testing on. It's running one version of Lotus, which is the current one, but basically it's really hard to account for all the changes that is going on, and therefore this will be kind of a point in time. So in part one we went through how to seal data on unmodified Lotus code, and that is still the principle that we're using today. So basically we want to try not to change the Lotus code as is. You can get optimizations out of doing that, but for me I think it's very important that we, instead of doing our own modifications, we try to push it back to the community and therefore change the Lotus code in itself from there. So examples of hardware configurations we're looking at that time, we'll get a little bit back to that, and also the balancing between workers, which was really the kind of the key to success at that early stage. So here in part two we're going to look at a reference design for a 1 petabyte raw storage provider setup, which will be able to seal around 3 tips a day. And I think it's getting more and more common that this is probably around what you can do per setup, and then you could obviously from there scale out if you need more capacity. But that's basically what we're going into. Another important point here is that I'm going to show and prove that it's now totally possible to do this both on AMD and Intel hardware. So in the last video it was really focused on AMD only for a lot of the stuff here, but now it's perfectly possible to do the whole stack on Intel hardware without much penalty. And we're going to talk about the storage market and how to seal real data, what that looks like, and how we do a backup. And I'm not a big fan of the idea that storage providers need to do backup. Basically we should be able to just lose the data, and because the client has saved that data with X number of different storage providers, it's okay that one loses the data and needs to rebuild. But the thing is, right now, as the network is still early, the collateral, so the price that we have to pay for each sector of data that we store, the collateral is quite high, meaning that basically for each storage providers it would be pretty high risk not to have a good backup in place. So that's why we have it for now, but I'm really hoping in the future that this will be redundant, because basically it will be okay to lose some data, as the redundancy is done on the kind of between the client and multiple storage providers. So first of all, I think it makes really good sense to see what happens when we go from committing capacity and into storing real data. So this example right here is basically about the setup that I'm going to show today. So we have 3 servers here in the bottom, and we have some different roles that is currently running on each of them. So just to keep it simple, if you can say that it's simple here, but trying to make it simple here, this is only about doing committed capacity. So committed capacity is not real data, that is kind of random data that we seal, but the reason why we do that is we commit it to the network, meaning that this will now be available for storing real data. The important thing about doing that is that it's a good way to make sure that the storage providers are actually able to onboard data when the real data is there. So this is kind of a way to get started. And obviously this setup would also be the setup that most of the early Filecoin miners would be using, because they would basically just use committed capacity to get storage power and therefore being able to mine blocks. But what happens here is that we have an internet connection out here, and basically all we need to mine and to store committed capacity is we need our daemon running over at the very left side. We need that to have an internet connection so it can sync to the chain and basically do the messaging needed for sealing data. Then in the middle we have one of our sealing workers, so that's a dedicated worker, and what that does is part of the processes for sealing, which is the add piece, which is creating the data. It's the PC1, which is the first stage of pre-committing. Then it also does the pre-commit 2, which is the second stage. And what I'm going to show today is I really like designs where we try to keep this on the same physical box, because when that happens, then we basically don't need all the high capacity networking, and we don't need two places where we store the same data. So I really like if it's possible to do it like that. Then on the very right side we have our C1 and C2, which is our commit 1 and 2. That's the one doing the snark proofs, and I think it's okay to do that on a separate box. The reason why I don't do it on this all in the same box in this setup is because I find it a little bit difficult when we go into the hardware how to balance it correctly on one machine, and that's basically because of when you get up to these sizes, then memory starts to become really expensive if you want to go really high density. So this is set up quite simple. You see the light, so the light color here going from the AP PC1 to PC2. Then it actually from there is you could say that the C1 and C2 process comes after that, but the thing is it's not really that much data that is transferred to do the snark proof, because that's basically just a challenge on the data that you're doing. So data flow, the real flow of data comes from the AP PC1, PC2, and then into the Lotus miner, which will then store it onto long-term storage. So I kind of pointed out here that the long-term storage, that is in all the nodes, and that's one of my key points here in building a small solo miner setup. Is it makes quite well sense at this small scale to try to make each of the nodes hyper-converged. So basically they both have the compute part, but they also have the long-term storage, and they all contribute to that. So that's the basic setup here for doing CC. Now what happens is that if we want to do real data, then we need to move into having another node on here, which is a market node, and the market node needs to transfer the data from the client and put it into the system. So here we go. This is adding the market node to the system, and basically it also needs the connection to the internet to do storage dealing. So that's basically telling working with the client to figure out what is the price and everything. And then we also have the physical data transfer going on. This can be offline and it can be online. So there's two different ways of doing it. Basically online means that it goes directly into the market node But the offline version means that you can just transfer it like a normal file transfer, and then afterwards on the market node you can import the data there. And the further we go, it seems like online dealing seems to work better and better, but there's still some development to be done there. So for really large batches of data, of real data, then offline dealing seems still to be the preferable way of going. It could also be that the offline dealing was simply because you would get the data in physical hard drives to import into the system. But this is kind of focusing on the online part, also because retrieval would probably also be online. And what happens is that you see that now the data flows from the internet, it goes into our market node. I also put Boost in there because that's probably going to be the next implementation of the market, and meaning that will take over. But data goes into here, and then it will be moved from there into the add piece worker, to the PC1 worker, to the PC2 worker. Then you will have the C1, C2 snag proof, and then it will move into the miner again. Once it's stored there, we would normally have both an unsealed copy and a sealed copy. The sealed copy is used for proving that we actually are storing the data. The unsealed copy would be used for fast retrieval. So that means that if the client wants to retrieve the data, they don't have to sit and wait for the unsealing of the sector going on, because that will actually be a reverse process of PC1. So this is basically all that happens when we need to move into storing real data. One important thing here is that you see that the market node here is actually not located at this same physical box as the miner and the Daemon. And the reason why is because importing data, meaning that it also needs to be validated, that's actually quite challenging for the server. And you could do it on one box and separate everything, but you need to be really aware of the hardware consumed by the market node, because it can use a lot of CPU cores when it's importing. And basically what can happen if you have everything on the same box is that if you have a lot of incoming deals at the exact same time when you need to prove your sectors, it could be that your CPU is actually overutilized, and you start seeing really slow proofs. And it might actually mean in the end that you could miss a window post, which would be very bad. And the other thing also seen is that if you import a lot of data, it can also be that your Daemon is not able to sync up. Basically, it just, it gets starved and stops syncing. And if you don't have your Lotus Daemon synced, well, you can obviously not send the window post messages as well. And the same goes for mining blocks, winning post. Also, you need to keep your pipe clean so you're able to actually provide those when it happens. It's really annoying, and that happened to me as well in the early days, that you could actually see that you were importing data and you started to do the winning post, and it came up and said that your computer was too slow. And your computer is not too slow, but basically because you were doing these deals, it was not able to provide the winning post in so few seconds that you were able to publish it out to the network, so you could get the block accepted. So that's why you would see that I try to put this on different servers, because obviously if you do this, then there will be no impact of whatever goes on the market side, will have no impact on your ability to mine blocks, to do provings of your deadlines, and also just to keep your chain in sync. And actually the same goes for the sealing. So that's why the setup looks like it does. And this gets more important the more stuff that you're trying to run. So basically, if you're only doing CC, that can be quite predictable. If you're doing online deals with real data, it might not be predictable exactly when these data packages are transferred, and therefore you could start to get congestion and you could get a lot of load on the CPU. So this is the main reason for trying to keep things separate. So next up is back to talking about the balancing of the sealing workers. So this is basically where we left off from last time. So up in the corner you'll see one of the slides that I did on the last video, which was trying to visualize how are we actually balancing stuff. And it makes really good sense to try to put it up like that and see, you know, what is actually the timing, how much capacity do I need between each of these different kind of workers. But there's happened a lot of things still since last video, which is in October 2020. So at that time it took about 10 to 15 minutes to do an add piece process that was running single core, so it was very predictable. That was fine. It was not the limiting factor. But today it's running multi-core, so now we can be down to 1 to 3 minutes. Normally it takes a little bit longer when you have real data compared to just having a CC, but the speed up is significant. PC1, one of the really important things here, it went from about almost 6 hours when we only had a single core SDR. Now we can do multi-core SDR, and basically we have almost doubled the speed. So that's very awesome. It uses some more cores, but we can basically control exactly how that operates. So that is a really good advantage. I don't think there is many designs today that would benefit from running the old single core SDR. There are some high performance AMD CPUs that would only be able to do a single core SDR, so you would be locked on that. But I don't think it's an advantage today, because basically you can get cheaper CPUs that can leverage on the multi-core SDR, and your total aggregated throughput would probably be just as good or even better. So on the pre-commit 2, then we get into the part that is using GPU. We went from 40 minutes around that, and now we're down to 8 minutes on a 3090 RTX. So that's really good. It's a brilliant upgrade, and what happened is that it's now running more native CUDA compared to before when it was OpenCL. So you have some more CUDA specific optimizations in the Lotus code, and obviously, yeah, that works really great if you have an NVIDIA GPU. So that's kind of the downside of it. Is like this is meaning that if you're running unmodified Lotus, well, you are pretty locked into running it on an NVIDIA GPU that can do CUDA if you want these kind of speeds. Then on commit 2, which is also GPU intensive, we also went from almost 1 hour and now down to 12 minutes on the 3090. So it's also really good. One thing to think about here is that with these optimizations, it also means that the GPU is running much harder than it did before. We actually in the or after the first video, but before this, where we started actually running 2 processes in parallel on each GPU just to utilize it better. So if you had a GPU which had 20 gigabytes of memory or more, so that could be the 3090 which has 24 gigs of memory, you would be perfectly fine at running 2 C2 processes at the same time. You can still do that. So that's not a problem to run 2 processes on the same GPU. The thing is that now that it's using the CUDA optimizations, it's running more heavy on the GPU, so the kind of the benefit of running 2 processes is not the same as it was before. And it might be that in the future we have so much optimization that basically it makes no sense to run 2 processes anymore. The good thing about doing that is also when you're running 2 processes, you also need the memory, the system memory of 2 processes. So if you could run 1 process and run it faster, that would actually be more beneficial than having to hit it with 2 processes at the same time just to get the maximum performance out of it. But definitely we're going in that direction, so that's really good. And obviously, coming from an hour and down to 12 minutes, it also means that the GPU part here is not such a big thing as it was before. So it's like the sealing hardware just gets less and less, and this is also obviously where we want to go in the future, trying to minimize the footprint of the sealing needed. So the same thing goes on with the CUDA optimizations for window post. This is the GPU part specifically. So in here I don't take into consideration the part about actually loading the data, because that can be very different depending on what kind of storage system you have. So what we're seeing there is, like, if you are on direct attached storage, which would be what I propose in this video, which might only be feasible for pretty small systems, but you get really good storage performance out of that, meaning that your window post will be blasting fast. But if you need to scale to a bigger storage capacity, obviously you need to distribute it better. And if you do that, then you will have to take into consideration how the speeds are for actually loading the data, because that can take some time. But this is the GPU part of it, and it is really, really fast now. So back from 10 minutes, you have 30 minutes to complete your deadline. That's a window. And basically, if you use 10 minutes just on the GPU, well, you didn't have that many tries. So if something did go wrong, you need to restart the miner or anything like that, you needed to do it first thing in the deadline. So coming down to only 3.5 minutes, it means that you can do like many proofs in the same deadline. So now it's just like it's not as demanding and challenging as it was before. For the winning post, it's just really, really fast now. We can get it under 1 second, which is good because basically we want to make sure that if we do get a winning ticket and are eligible to do the winning post, we want our message out there on the network really fast to be sure that we're not getting any issues on getting the block out there. So the conclusion here is that pretty much everything in the sealing process goes much faster today. One part of it is because the hardware is getting faster. The other part of it is because basically the Lotus code still has some optimizations left in there that can be utilized, and there will also be future optimizations, of course. So this will only go faster and faster. But the main point here is that being able to balance, like we did in the first video, being able to calculate, so what is my throughput for each of the stages of the sealing, that is still the same concept, and it remains the same. So we'll still have to think about that. We need to make sure that we don't create any bottlenecks through the process, because basically this will be like like the lowest bar. So whoever part of the sealing process is the slowest, well, that's how fast we can go. So moving on from there, we will actually start to look into the reference architecture. And I'm going to start with some different ideas of what you could use. And let's just get on to it. So this is for the Daemon, the node, the miner, and for the market as well. Not because it needs to be on the same box, but this is kind of the hardware that I would use for those kind of systems. So first of all, I have some different components here that I like, that I wanted to point out. For this setup right here, it's kind of a home build, you could say. So it's a chassis and it's a motherboard, which could be ATX or extended ATX. And then you have some GPU, CPU, memory, and so on that goes on top of that. Obviously, you could also buy real rack servers, like integrated servers, where you have everything in there. It could be a bare bone, or it could be obviously just a fully spec'd server. Here I'm using Supermicro as reference, but it could be any of the big brands, because they all provide this kind of hardware. This hardware looks very much like what you would buy if you do AI, machine learning, stuff like that. So it is common hardware, But what I'm trying to do here is more set a reference for what kind of sizing would you go for. So starting with that, the Supermicro chassis here is a 24 bay chassis. I like it very much because it has those 24 bays which can hold our long-term storage, because this is about doing storage, right? But in the back you also have two little drives which can hold some, basically that would hold the OS drives in RAID 1. And that's cool because it's also hot swap, so you don't need to take the node and everything offline if you do have a hardware failure on that. So the other thing is, like, this comes with redundant power supplies, and also just it is like full height, so it can take pretty big GPUs in there as well. So on the motherboard, I kind of put up two different examples, one being the AMD based, the other one being Intel based. Now for Intel, also on the node and the miner, it makes really good sense to have a CPU that can do that has the SHA extensions, because we also need to do some crypto calculations on there. So there is a speed up on the node if you can actually do that. And if you want to go to something that can also have a decent amount of memory, then on the Intel side, you would basically need to go with the Intel Xeons 3rd generation scalable CPUs. It can also be the W CPU, but it needs to be one of these versions that's on the 3rd generation. So that would be Ice Lake. And you could also obviously use consumer hardware here, so that could be the new Lake, and there's actually also some of the others that can do this. But you will pretty soon get into a memory limitation, and that's basically why you're looking at server versions here. On the AMD part, it would be the EPYC CPU I would choose. I know a lot has been running the Threadripper, and the Threadripper Pro is out there, which is really competitive to running an EPYC for this. The concern I have about running EPYCs is that the Threadripper, is that it's the TDP on these CPUs are quite high because they're clocked high. We don't really need that. So it's like, it's not really efficient in terms of how much power it's actually consuming to do the task. And the other thing is, like, most of the Threadrippers, they would be limited to not that much memory, maybe 256 gigs of memory. That's okay on these systems right here. But I would prefer, if you were running that at least it's a ECC memory, to make sure that we are not getting hit by any corruption of data or anything like that from the memory part. Another thing to look out for, I'll actually go back to them when we see some pictures, is that the reason why I like the EPYCs and the Intel Xeons is because mostly the motherboards would be lined up for a server setup where you have decent airflow, and that's quite important when we start sealing really hard. So I'll go back to an example on that, and that could also be why I don't really like using the consumer stuff like Threadripper and so on. It is cheaper, it provides some performance, but if we are looking at building a reference design here for a 1 petabyte miner that needs to scale maybe even further in the future, I think we are better off just using these kind of components. But that's my personal view on this. So on the GPUs, on a miner, that's basically for the miner that would need that to do window post, I would use one of the Quattro RTX Ampere versions. And reason why I would do that is because they have extreme low power usage for what they're performing. I really like the A4000 because it has such a low footprint. It uses only a single PCIe connector for the power. It's single slot, It has a decent amount of memory there, and actually it has a really large amount of CUDA cores, which is not running fast, but we don't need that. We still get those blasting fast speeds. So when I'm talking about 3.5 minutes for doing a window post, that's actually on an A4000. So it does a better job than the old 2080, and it does it at like half of the power usage. And that's, I think it's a really good thing in a miner that needs to run all the time, that we try to lower the kind of the energy uses, and not having some like oversized hardware in there where you take like the overhead of running it, but actually it's not really needed for the job. An alternative to running these two A4000, and the reason why I would have two in there is basically because right now we have the winning post and the window post running on the same process, but very soon we will have those in two separate processes. And the thing is, like when you do a window post for those 3.5 minutes, when you do that, and if you have many deadlines, every time you do that, the miner is actually not capable of providing a winning post. So if you get a winning ticket at the same moment as you're doing your window post, you have the ticket, but you can't provide the proof. So that's really annoying, because that does happen sometimes, especially as you move to bigger sizes of miner. It does actually happen, and that's super annoying, because you just see your block reward just get lost there. The reason why you can, I want two of the A4000s or one A5000 is the A5000 is big enough to run two processors on there for sure. It's probably a little bit oversized, but that's also okay. But the thing is, like in the future, we will have a separate worker for doing the window post and winning post, meaning that we can separate them. And we can shoot both at the same GPU. We just need to make sure that the GPU will run both, and not just say, hey, you need to wait for my window post to be done before I will do your winning post. Because at that time, it will be totally over. You know, we'll be at the, I don't know how many next epochs will be there, but you know, that's done. So just going back to these two motherboards. So what I like about these motherboards, if you are kind of the home builder style, is that they do have some integrated stuff on there. One thing is like they already got the 10 gig networking on there, so that's on board, so you don't need to buy a separate PCI Express card for that. And the other thing is it also has a SAS controller. And I actually ended up using SAS for my OS drives and also for my long-term storage, but I really like it on the OS drives because it's kind of a RAID 1, but it's kind of out of band. So I'm not using Linux or anything integrated in there to try to make a RAID. What happens is like when I have the hardware controller here, the RAID information is on each of the drives. So if I have a hardware failure on my OS drive, it will light up on the back of the server. If I replace it with a new drive, it will basically just rebuild, and I don't have to touch anything in the actual like in Linux. And I like to keep that separated, because although that you can do like a poor man's RAID in there, the other thing here is just more safe. And basically what we want to try to do with the miner is to really keep it online as much as possible. And this is not really an expensive thing to do. So I've ended up just using two SAS 3 drives. So it's not on the NVMe protocol, but obviously it's an NVMe drive, but running on the SAS protocol instead, because then I have my perfect RAID 1, and I also have the kind of the speeds from NVMe. And that's pretty good when you have the node, so the chain data syncing up on there and so on. So it's not as fast as if I had the chain data on an NVMe, but on the other side it's on a hardware RAID 1. So I find it compelling to do it like that. So that's basically all I wanted to talk about for the miner and the Daemon node, and this could also be for the market node. That's kind of how I would spec those. And we will get into detail about specific CPUs and so on afterwards in the example. So let's move on to a combined PC1, PC2. This could also do C2, but as I said before, the C2 is more like that's a challenge, doesn't really need that much data. Where the problem about is, having PC1 and PC2 separate is that if you run a 32 gig miner, then basically that expands into 11 layers, so 11 times that, and then you also have additional data on top of that. So in the end, you end up having like almost 500 gigs of data, which is expanded from PC1 and then needs to be moved into the PC2 process to finalize the job. And when you keep that on the same server, then you don't have the get process, so you get rid of that. And basically, you don't need to wait before the PC2 can be executed on it. So the waiting time is not the problem in itself, because that's not taking up any compute resources, but it's definitely taking up a lot of storage resources. So that's why I'm trying to come up with design here where we make sure that, yeah, we have a PC1 worker which is set up for that, but it can also handle the PC2. So again, you have Intel on one side and you have AMD on the other side. Ideally, I work with single CPU setups. Reason why I do that in these kind of small miners storage providers would be because it's basically just more efficient having a big strong CPU, maybe running at 200 watts or something like that, compared to just having the double and not really providing more performance. Obviously these CPUs are more expensive, so it really comes down to what prices can you get. But in the end, the reason why I came up with two different designs here is also because right now, with all the scarcity on hardware, it really comes down to what you can actually get your hands on. And that's why I said, if you can't get a single CPU board like this, you could obviously also go with a dual processor board. And the thing is, the main thing is, like, if you want to go with a single CPU, you probably need 16 DIMMs with that to be efficient. If you go with a dual CPU design, then you probably can do with 8, and you would also do with CPUs being on a lower performance CPUs, lower cores. But still, these are some different examples of the motherboards, and I mainly just use the Supermicro in here. The Asus there is actually one of them that I've been running since Space Race. It's kind of an odd design it has, but it works quite well. I use that OCP2 connector there right in the middle next to the CPU. I actually use that for my NIC, so that's where the NIC is sitting, so it's not taking up a PCI Express lane. It's kind of hard to fit GPUs on there because the DIMM sockets is kind of in the way of most of them. But still, I find it possible to work around. But there are some design issues when you are doing these kind of extended ATX designs, where obviously if you're just going with a normal bare bone server, then normally it looks a little bit more available. And the other thing is, like, if you are doing a bare bone setup or like a full spec server, you might go with a dual CPU server which has 16 DIMMs each, so 32 DIMMs. And then basically what you have is just the double amount of my single setup here. So I'm not saying that this is like you should go in exactly this direction. I'm just trying to put out some principles for what it could look like. And this is probably a good way to go. Again, we have the same with the GPUs, that we might want to use two of the A4000s. We could use one A5000. If we want to go to bigger setups, we could also go into the Tesla GPUs and so on. These are quite expensive, and there's a big additional price tag to going with the Tesla cards. The benefit of doing that is, like, you can run even more processes at the same time, but it's just like for building a simple setup like we're trying to do here, this would probably be the preferable setup. And again, reason why I'm going with these these GPUs is because they have a lower energy footprint, but also because they will actually fit very well into most servers. And if you are into using gamer GPUs for your first rig, that's fine. But be aware when this needs to be moved into a server setup as you start to scale, those GPUs will probably not fit, and they will be using too much power to get rid of, and they will basically just have a physical layout which is not compatible with the server. So that's why I would go with something like this. Although if you compare an 8000 to the 3090, which I'm also running in the test, it's not as performant, but then again, it's still okay, because as we just saw, the speeds on the GPU part of the proving and the sealing is much faster now. So this is basically all I had to say about this setup. We're still using the same chassis here because we still need to have the long-term storage in front, and then basically we have the sealer running in the back up there. And how we put this together, it comes back to that original idea of how we balance the different workers. Righty. So I also included a backup node here, and the reason why I did that was back to the thing about that we probably shouldn't have backup, but then again, right now, because we have to pay collateral for each of the sectors that we seal, and if that is if that's real data and it's what we call verified data, we actually get 10 times the collateral. We get 10 times the storage power for the sector, but we also have to pay 10 times the collateral. And that's kind of the key thing here now. So if you have a 32 gig miner, that 32 gigs of data, you now have to pay 10 times as much collateral for that. So actually you have quite a lot of dollars in collateral for that piece of data. You basically need to secure it and make sure that you don't lose that, because that would be pretty bad if you lose it and not being able to prove. It will get terminated in the end, and you'll basically lose that collateral. So right now, incentives is pointing at that you need to have some kind of backup solution. So what I'm proposing for this setup is a backup miner that I'm using myself, which is located at a totally different physical, it's another location basically. And reason why I would do that is because my backup system here is not only backup of the data in itself, but basically this backup node is set up to be able to prove my data. So say that I had a major disaster at my main site, I would basically be able to use my backup server to prove my data, to run through the deadlines for every day until I have my main site working again. So this is the idea. Obviously you could also just store the data and say, yeah, I just have a backup of my data. You could even have a cold backup of your data, saying like, if shit happens, then I will go and copy back. You should just be aware that if you are in like the 1 pip size, it will take you a lot of time to actually copy data back. So this is why it makes really good sense to have something that can actually prove from where your data is stored, the backup is stored, and then you can do the copy job at the same time. Maybe stop it while you're proving, but basically you need to be able to be proving, because otherwise it could take you maybe like 2 or 3 weeks to copy over the data, and you can't prove your deadlines while you're doing that. So you're just getting slashed every day, and you still have to do all the copying and everything. So it's like that would be very, very stressful compared to just having a backup site saying I'll just prove from here, I'll copy over the data, and I get back to my primary site once that's done. Again, I'm using kind of the same hardware here. The only difference is that I'm now using a 36 bay server. So I'm actually using that, and what it means is like now your compute part in that server needs to be low profile. That has some implications on the GPUs that you can use. What I found is like I'm using a little T4 Tesla GPU, which is quite expensive, but also quite performant. And that's actually quite funny with these kind of GPUs. Is like these very small GPUs. Like this is like a single slot. It's low profile. It's very tiny. It's only using 70 watts of power, but it's still perfectly capable of running the window post and stuff like that. So it's like you don't really need that much to go, and this could also be something that could be sitting in your main miner. But again, the reason why I would probably not go with something like that is because basically it's just too expensive compared to what you actually need. But for something like this, you would probably need to go with something like this. An alternative, which is coming up now, would be the NVIDIA Quadro A2000. The 2000 is an awesome little low-profile GPU. It's using 2 slots, so it's not the official low-profile, but it can totally fit in there. But you need the 12 gig version, which just came out. And reason why is because when you do your window post, it is still consuming up to almost 10 gigs of video memory. So I would prefer to be using it on a 12 gig and not do any fallbacks or anything like that, so you have the full performance. Also, we will see here in this year the A2 coming out, which is also really like low on CUDA cores and everything, but probably still very well performant to do this kind of task. So this is the setup. Connection between the backup and the main side. I haven't gone too much into that, but I would probably advise to keep it on a 1 gig fiber for that. So basically you could do with 500 megabits or less, but you should be aware that if you're sealing with 3 tips a day, you know, it also takes time to actually copy that data over. So you could have a setup, you could end up with a setup where you're actually sealing faster than you're able to back up your data. So now you just have a cluster where it's not really backed up correctly because you haven't been able to move over the sector. So keep that in mind when you scale. Okay, so this is just an additional slide on the how we put together the different workers on each of the machines. And the thing that I want to do here is I really like to combine my app piece, my PC1 and PC2. PC1 and PC2, we talked about that before. AP is because that is where you kind of generate the data and you pack the data from your market node. And once it's there, it kind of just makes sense that it's at the same physical location as where you now need to do the PC1 and obviously also the PC2. So what I'm lining up here is now we're actually getting into some different versions of CPUs that you can be using. Some of these I have been using. So the 7702P is actually running as one of my sealing workers right now. And I find it like for the last year it has been probably the most performant setup, but it's also a really expensive CPU. So it's like, of course, if you can only get it for $10,000, then I probably wouldn't go with that. But if you could get a bargain like secondhand or anything like that, it would be an awesome CPU to use for a setup like this. Basically because it's a single CPU, but it can do 15 PC1s in parallel. So that gives you a lot of throughput on the PC1, which can be the limiting factor right now to really get some throughput on. So that's really awesome, and I'm running at that now with 1 TB of memory. So that's what you need together with that. But say that you can't get your hands on that, you might want to move into one of the newer CPUs, which is Milan. Well, it could also be this other version, which is the 74 F3. There are many different CPUs right now, but one reason why I like that, I know that it's using a bit more power, but it could be that it's available. So again, back to the available thing. But it will be probably blasting fast at doing PC1s. In a dual CPU setup like this, each of these CPUs has 8 compute complexes. And the compute complexes is pretty important when you do multi-core SDR, which is how we get the high performance. Basically because when we do multi-core, these multiple cores need to be in the same compute complex because they need to run out of the same layer 3 cache. So what happens is, like on a CPU like this, you have 24 cores, but it has 8 compute complexes and it has 3 cores in each. So what I've done here is, like, what you probably can't see really clear is, like, for each of these different designs, I basically point out for each CPU, for each thread, exactly how I would lay out the different processes. So on a CPU, like we just talked about, I would probably run it with, so it will always have that one master running the SHA calculations of that PC1 job, but I would probably combine it with the 2 producers. So I'm using up now all 3 physical cores in the compute complex. But on the other EPIC, the 7702P, I would actually just run it normally, which would be having like 1 master and then 3 producers. But you can actually control this yourself. So the reason why I bring it up is because this is really important if you want to go into some of these systems. And using multi-core SDR is you need to be aware of your CPU topology. I would say it's going really deep into the technical part of a CPU to figure out exactly what it looks like. It's not really rocket science. It's just like you really need to go really nerdy into exactly what does the CPU look like. But I'm imagining that this is just because this is where we are today. So probably we'll see in the future that Lotus can do more of this in the future and basically say, okay, you got a CPU looking like that. I would probably seal like this, and you don't have to care that much about it. But for now, having a setup like that, you would have to go in and say, hey, you can only use 2 producers per job, because otherwise you would start getting over each compute complex. That wouldn't work. The Xeons on the other side is very much different from an AMD. They basically have one shared layer 3 cache, meaning that now you have 1 compute complex. That's basically how we look at it. So you're not limited by figuring out how you can fit these different processes into each compute complex, because there's only one. There's only one shared layer 3 cache. It makes it kind of easier, but then on the other hand, most of the Xeons does not have the same amount of cores, so you might have to reduce it even further. So for most of these, I would only run with 2 producers just to get the maximum throughput. And there are some different SKUs. So the 8368Q, that's a really high performant CPU, and it has a pretty high power usage. So that's of course not so beneficial, but it's also very fast. But it's one of the CPUs that I have actually been testing this on, and I know that this works really well. And one of the key findings from that is that I can run it with 2 producers, but I could actually also go down and only have 1 producer. So now I'm only using 2 physical cores for each PC1 job, and I did it at almost no penalty. So we're still in the realm of 3 hours 30 minutes if I do like a ton of PC1s in parallel. So now your limitation will probably not be the CPU in itself, because it has a lower amount of cores, but it will probably be about how much memory do you actually have. And the thing is, like for each of these PC1 jobs, we need those 65 gigs of memory. So you will probably be limited if you are into 1 tip of memory on your board. You will be limited to only doing 15 PC1 jobs. But that would be totally doable on a single CPU setup like this. You can also do the dual setup. The reason why I'm trying to keep this to 1 tip of memory or 2 times half a tip of memory is because with the amount of DIMMs that we have here, we keep it at 64 gig DIMMs. And the reason why I do that is because moving to 128 gig DIMMs, that is totally possible today, but it might be that the price premium, basically what you have to pay to get these sticks, It's just like it's a big step up, and it's not ×2, it's more like ×3. I know times are changing. This will probably change in the next half year or so, but for now it can be really expensive still to buy the big capacity sticks. And that's why I'm trying to size this after saying like, yeah, we need to keep it at using the 64 gig memory sticks. That just makes most economical sense for now. But obviously as we go bigger sizes, we can go more dense, we can do even more PC1s in parallel. And it's really interesting to see something on the Intel here that you can even go down to one producer only. On the AMD, we could potentially go down to having having less producers, but the current issue right now with Lotus that we are currently trying to fix is like if you move past having one PC1 job in each compute core complex, then it doesn't really act up nicely. So that's a multi-core or it's a multi-core SDR issue that we probably just need to fix. And if that happened, then potentially on the 7702P, it has 4 cores in each compute complex, so you could say why not just run 2 processes in each. It could run 32 PC1 jobs on one CPU if you had the memory. But what is important to also think about here is like you also have the other processors that need to run on here. And one trick that I really like to use is to keep the SMT on. So you have the hyper-threading or the SMT still running on these CPUs. The multi-core SDR makes sure that it's only using the first thread in each CPU core, so it's not using both threads of the CPU core. That would be pretty stupid if you're trying to do PC1, because they would basically need to go both at full speed and you would end up having half speed for each. So we don't want that. But what we do want is for the AP process, which is a multi-core process, and for the PC2 process, which is also a multi-core process, we would like to kind of utilize some of this part of the CPU that is not so heavily utilized. And what happens is like when you run with the 2 producers or 3 producers, it's actually running at maybe like 40% or 20%, something in that realm. So it's like it's not really using the full capacity of that core that is running the producer job. So if you have the producer job running on the first thread in each CPU core, then why not use that second thread to do something else? And that could be the AP process, so that's what you see here in the light red, or it could be the PC2 process, which is here in light blue. And basically what you see is on one side you have the green, which is the master, you have the yellow, which is the producers, so that's the first threads of each of the CPU cores, and then the second thread of them, you can have different stuff going on there. But one key thing here is like if you look at it here, you can see that I'm never doing anything on the second thread of the master. So where I have the PC1 SHAR calculations going, that is always hammering at 100% load. I would never want to have anything happening on the second thread, because that would basically reducing my throughput of my PC1. Where having something else going on the producer threads seems to have very little impact on actually still performing on the PC1. So that's one thing to look out for if you want to go into these kind of combined systems, is that you can actually utilize some of that. In the end, the optimal would be that you have your CPU running 100% on all cores at all times. That's probably hard to get there, but at least this is one of the ways to actually make that happen. So that's a lot of the optimizations on the actual node and how you can do that. Then we're moving into the summary, and I guess this is actually where you could say that we're looking at what is actually the reference architecture here. So I'm just moving this over here so we can see what goes on. So basically in this setup, which is the full 1 pip storage provider setup, you would have 3 of these 24 bay servers sitting next to each other, and then you would have your backup miner or backup node, you would have that offsite. So these 3 boxes will do a lot of different things. So first of all, our first box there will be obviously the storage. So you have 24 drives in there. I put in some Western Digital. I use the Ultrastar, but obviously the Seagate Exos is also very used in the community. So it's like, I think for some of this hardware, you know, I can come up with some examples here, but it really comes down to availability, because hardware right now is so scarce. So it's like whatever you can get there, if it's a single CPU, dual CPU, if it's one or the other hard drive, probably you're better off buying that if it's a good price, compared to just sitting and waiting, because you know you don't get anywhere if you just want the perfect setup and you can't get the hardware parts. So that's why I want to keep this a little bit open, just to say that you have to be pragmatic about getting hardware these days. But at least 24 drives, that's actually in all of these. And then you have your miner, you have your daemon, and then the storage in itself sits on the first server there. There's also a different specs on what CPU you could use up there. I use I actually use the 7302P, so that's a 16-core EPIC. It's an older version now, but it's like perfectly fine for doing that. No issues there. You could also have a higher, like a higher core CPU, especially if you also want to put some of these stuff together, like having the market node on there, still separating it, still reducing the amount of cores that it can actually use. But you know, the more you put on there, make sure that you have enough cores. Then we have the GPUs, as we talked about. We have the networking. For a setup like this, I said before that I'm actually doing a direct attached setup here. So how that works is, like, instead of having each of these servers running like a NAS on there and doing like a network based file storage, instead I would direct attach the SAS cables. So how I do that is basically I treat my 2 other servers here as JBots, and I know some people might say, you know, that's kind of risky, because if you turn off that server, your JBot just got lost. And basically my counter argument for doing that is, like, I never turn them off. I would, if possible, I would never turn them off. If I have a hardware failure and say just, you know, power offs, I would make sure that I have the full array on each of these. I wouldn't split the array between each of these JBots, basically because if you have half an array, you might have your RAID software there trying to rebuild or start to do something that it should not do. So better just lose it all. Just have it offline and just saying, like, when I turn this on again, it will rediscover that, okay, there was my array. So that's one important thing, but I don't really consider it that big an issue. From an operational perspective, yeah, it could be an issue that if I need to do service on one of the other nodes and I need to turn it off, then obviously I would also need to turn off my my first node to that. So I need to turn it all off to kind of replace hardware. Again, my counter argument for this is I really want to build this part of it so I never change any parts, basically. So this can just run for years. Obviously the hard drives and everything like that would be replaceable without turning it off. So that's hot swappable, the fans in there and so on. There is some stuff that is hot swappable, but for the CPU and so on, I would, you know, this just needs to run as is, no changes at all. So that was the first machine up there, and it's running the Daemon, it's running the miner. It has these different roles called mining, sealing, and sector storage. I'm not having the markets on there, as I said before, but it could also, yeah, it could also be on there. Talking about the storage here. So if we have 24 drives on each of these machines, I would probably set it up as 2 arrays on each of them, so having 12 disks. could be RAID 6 or similar, so having 2 disks that can fail, so 2 disks of parity, and then 10 disks which would have like usable storage. So I would lose 2 disks on each array. That would be 4 disks for each. Basically, if I have 6 of these arrays on these 3 boxes, adding it up, taking a little bit from doing the partitions and everything, I have about 960 gigs of raw capacity on there where I can actually fill in sectors. Now, if I'm doing verified deals on this, and that would be my proposal, you know, go for the verified deals, try to get as much storage power. You also spend more on collateral, but you use less on physical hardware. So basically your footprint will be much smaller. Your physical footprint will be much smaller, but your storage provider operations will be larger and your storage power will be larger. So if you go that, like saying like I only did verified deals, and you have the fast retrieval, so you have the 2 copies, so you don't need to do the unseal, you'll probably end up having almost 5 petabytes of adjusted storage power on a setup like this. So that's kind of a lot actually, having from a system which is only like right here, there's 12 use in total, 3 pretty similar boxes. So if we move on from the daemon and miner down to the market node, the thing about that market node is that it actually has a double amount of memory, and why we have more memory on there is not because of market node, because that's almost using no memory, but it's because we want to do the C2 on that machine. Now, as I said, C2 is kind of lightweight on the networking, but obviously it needs a lot of resources on the CPU and also on the GPU. And basically what I propose there is like we would run 2 C2, C1, C2 workers on there, and basically point at each GPU, if so only one GPU at a time if it was the A4000, or point both processors at the same A5000 if there's only one GPU in there. And it needs those almost 200 gigs of memory, each of these processors, so there needs to be plenty of memory on there. I just pointed out here that it would probably take about 20 minutes to complete 2 C2s at the same time, even if it's on the same CPU or GPU. And that said, we are at about the capacity of about 4.5 chips a day. So we just need to make sure that we keep that high enough to keep up with the PC1. That's basically the main point here. So another thing is, like, you also see that this has some storage there, which is a bigger partition for the Lotus markets currently. You also see that I'm using 8 chips drives on that, so that's obviously a pretty expensive drive to use, but the reason why we do that is basically because online deals and offline deals, they would probably need some caching. And yeah, you could put it on a single drive, or just put a single NVMe in there and just say like all the data that I'm caching here for importing, I'll just put it on there, that's fine. It's just like, if you lose that disk, that's just annoying. If you're working with real clients on the other end, you say, hey, I screwed up your data and now I need to download it all again. It's like, yeah, okay, that's probably not so serious. It's like, that doesn't sound like you're really a secure place to store your data. So although your long-term storage might be fine, then it, you know, if you lose your data while doing the import, it's like, it's just not annoying if you have to go back. So so that's why there are some RAID 1 storage there for the caching as well. Obviously, this is not a hard requirement, but that's just how I like to set it up. Then we have the sealing worker, which will do PC1, PC2. So just like we talked about. And I set that up here, both with an example with the Epics and the Xeons, both with the single CPU and double CPU, because basically you can do all that. But again, if you do the dual CPU and you do it in a setup like I proposed here, you are going to have a bigger overhead on your power usage. Probably having a dual CPU setup, you can buy a much less expensive CPU. So it could actually be that on your purchase price and the availability, you would maybe be better off doing a dual CPU setup, basically because you can't get good prices on the single CPUs because they need to be really high end, and also because it's just it might be just cheaper and more available. So what happens here is, like, if we say that we can do somewhere in the realm of 12 to 15 PC1s in parallel on this box, and they will take about from 3 hours 10 up to maybe 3.5 hours, you are looking at just around in the area of 3 chips a day. And that is going to be like your limiting factor of the ceiling cluster. So you could say if it's a one CPU setup and you can do 3 chips a day, well, probably that's about our benchmark right now for how fast you can go. And if you do something optimizations, you buy a higher end CPU and so on, you might be able to tweak that up to almost 4 chips a day. But that's, that's just really pushing it. And again, if we're talking about verified data here, you times it by 10, it's still a lot that you can actually seal. So if we say that our reference is around 3 chips a day, you could have a dual CPU bare bone. It could probably do 6, because now we would have like 2 CPUs, high performance CPUs, and you would have 32 DIMMs in there. So it's like per CPU you could probably do around 3 today, and maybe if you optimize really much up to maybe 4. But that's basically what we're looking at. And if you want faster sealing than this, you could totally go ahead and just buy one more of these workers. You just need to make sure that you can still provide the C2. So on this box, I'm also doing the PC2, as I said. And the thing is, like, if we run 2 processes, it doesn't use that much memory to do, so it's not really a concern, the memory. It does use some of the CPU, so you need those additional steps that I talked about. You need some of those available on the CPU. So if you're doing an Intel setup with only one master and 1 producer, and you're doing that on all available cores, I'm pretty sure you won't have available capacity to actually do your PC2, or you will see a decrease in your PC1, because if you're only running with 1 producer, it's going more like 80% on that load on that. So like, if you optimize your PC1 really hard, so you're using all your CPU resources, and obviously you don't have any CPU resources left to do PC2. So that's just something to take into consideration, that if you want to go with something like that, like really performing really high high consumption on the PC1, you might be better off just doing individual PC1 and PC2. But that's kind of not the point I wanted to make today. But we see that if you do 2 PC2s on systems like this, you could do 2 processes at the same time on the GPU, and or as you said before, doing the A4000, just put 1 on each. But you will end up with a pretty high capacity there. So again, probably the limiting factor here will be the PC1, as long as you go with these kind of size setups. So that will be probably where we need to do the tweaking. And the really important thing here is, like, we need to make sure that that we have enough PC2 capacity to always keep up with our PC1. So that's actually one of the key issues around having a combined sealing worker like this is, like, what happened if our throughput of PC1 just doubled. So now we can do 6 chips a day, and now our GPU is not fast enough. Well, can I fit more GPUs in there? I might, but also it could be that I have a design where I actually can't fit more GPUs in there. And now I have a problem, because now I can do some of the PC2 on the node itself, but I would actually have to transfer some of it off the server to do that. And that's a little bit annoying, because if you do that, it's like now you need the networking, now you need the double NVMe and everything to do that. That's kind of what we're trying not to do. So the backup node here is basically the same. It has more drives in there, and the reason why is because if we have 6 arrays on those on the main side, and each of these 6 arrays has all the verified deals and the fast retrieval, then it actually has kind of the double the physical storage. So what we need our backup node to have about half of that, because we don't need, well, if we were really nice, then obviously we just had a full mirror of the main site. But the thing is, like, if our main site, you know, total disaster there, we don't need the fast retrieval files to actually prove our data. So as a bare minimum, we need the sealed copy, and the sealed copy is in the sealed cache folder and also the sealed folder. But it's important to have both of those. But we don't need the unsealed copy, and therefore my backup site is basically half the size of my main site. So that's the idea. And if you start to make your main site bigger, well, you could obviously just buy more of these backup nodes. You could just make one of them being like the one having the capabilities of actually proving storage. So that's basically it. Again, I put some hardware in there. I have the T4 in there, and yeah, it's a little bit more expensive having those low profile GPUs, but the A2000, the Quattro A2000 will probably be a good fit here when it's really out. So that's basically it. So that's it for the full setup. Now, what I wanted to touch on is, like, I already grayed out on the ceiling worker that, you know, you might not have those 24 disks in there. Reason why, because today I actually don't have that. So I don't have that full capacity of this system. I just know that, you know, I could do that if I liked to in the same setup. But just to go from there, this is kind of the full setup. I would probably say that unless that you know that you're just gonna hammer it and just get that full 1 pip and then you just go on from there. Obviously you could, you know, put in the orders for something like this. Again, this is not a setup that is designed to go from 1 pip raw to 10 pip raw to 100 pip raw. If you know that you're going to 100 pip raw, then probably you want to do like a network setup from the very beginning, because you know your storage will never be direct attached. That would be crazy. So basically you need something that can scale out really nicely without any bottleneck. So think it right from the start. But if you want to be in the realm of this like 1 pip size, maybe less, this could be ideal. This is a very efficient setup where you don't have more servers than you need. I try to go by the kind of the idea that I want the least amount of power supplies in there. The more power supplies I have, the more overhead, because you would have motherboards and stuff like that, and it's all just overhead and overhead and overhead. So the more you can put things together, make sure that you're using your resources. Like the ceiling worker is not spending any resources on having those 24 drives in the front, because they will just sit on a SAS a SAS direct attached up to the main miner, so it doesn't even touch the system there. So there's no overhead in that. And that's my general idea. So if you have a dedicated NAS server standing next to this system, they have CPUs, they have memory, they use a lot of it when they transfer data and so on. That's just overhead and overhead. So for small setups, I would definitely go with something like this. But if you are to start at a small scale, which I think makes totally sense, then you could also go on something like, if we jump to the next, it could be something like this, where now what we did was we got rid of one of the servers from the main side, and that was basically the separate market node we got rid of. So just saying, like, okay, we don't need that to be running on a separate server. We'll just separate it out on the main miner, and that will be fine, because we just upgraded the main miner a little bit. If we do that, then obviously the market process and the C2 process we had before, well, that needs to move to somewhere else. So now we are in a setup where we only have like the Daemon miner and Lotus and the market node. Well, so the C2 and going on the first node. So let's just get back to that. So we basically took out one server. We reduced the amount of hard drives from 96. So that was like fully occupied on the whole system, and then down to only 25. So now we actually only have the miner node, and the Daemon is actually the only one that has hard drives in, only the front there. So 1/3 of it. That also means that on the backup node we can go down to only having 12 drives now. So that would just be like 12 drives in the front, half of it filled up. And also I would probably not have a GPU in the backup server because it's quite expensive. If I needed to prove, then probably I could get my hand on some kind of GPU that would be able to do that. So it's more from a risk perspective that's saying like, yeah, now I'm not really able to just prove my data like hot if something happened on my main site, but probably in 24 hours I would be able to come up with a solution because I do have the data available there. So I would be able to come up with a solution so I can start proving my data again. So it's like saying like, yeah, it's nice to have that GPU on there, but on the other hand, it's also quite expensive to do that, and we could probably leave that out if we just like need a really minimum starting setup. But what I do want here is like, what I also put here is like, I would like to keep stuff separate. So I know that a lot in the community there is starting with a single setup, basically having a single rig. So you have your miner, your Daemon, you have your sealing worker running on the same system. It's all using the same GPU. I find that really nice if you want to just get started with Filecoin, but I would definitely say go and do that on one of our test networks. That could be Calibration or the Butterfly, or it's just don't use real fill on that, because in my experience what happens is that if you have a single setup with everything on there, you can be totally fine if you are able to separate the processes. So running it in containers, running it with the task set, making sure that it's not using up too much resources. But if you have a PC1 process running a little bit wild, if you have too many C2 processes running there, and your miner is not able to handle your window post, you lose all your power. If you have a winning post coming up, you lose your block rewards. And in the end, if you look at the hardware cost here, if you're talking about going on mainnet and real data and everything, it's just not worth it trying to do that on a single machine unless that you are like totally pro of how you separate your processes and making sure that they won't eat up your Daemon's ability to sync the chain, or your miner's ability to do window post and proving your deadlines. If you can do that, awesome, do a 1-box setup. If you're not totally comfortable with setting that up, better go with 2 boxes, just making sure that you have your Daemon and miner running. It can also do the C1 and C2 on there. But if we do that, it would be because we're running the 2 A4000, so we're running the 1 A5000. And as these are 2 different processes, we would actually be able to, do a C2 and at the same time do a window post. But it won't sit there and say, I have to wait for the C2 to be done. So I'm pretty comfortable that this setup will work fine. I'm not using it right now because basically I want to keep those things separate. I don't think it's worth it trying to jeopardize your proving deadlines or generating block rewards with just cramping it all together, not like this. But the thing here is like we are offloading our C2 to our main miner and saying like, yeah, you can do that as a separate process. You just need a double amount of memory. And it can do about probably about 2 tips a day if you do it like that. Then on your other machine, that will be your old sealing worker, but it also has a market node on there. Again, using that high spec CPU or using the other designs that we talked about, you will still have that 1 tip memory in total. So now you probably need to reduce a little bit on how many PC1s you're doing, because you're probably locked in by how many tips you can do. because now you also need to do the C2. So the thing here is like if you will have 1 tip of memory in total, now you also need to do one C2 on that same machine. It eats up those first 200 tips of memory. So now you only have a little bit over 800 tips of memory left to do your PC1s. So now you can't do 15, now you probably have to do 11, 12, something like that. I have been running this setup for a long time now, having 1 tip of memory, having that 7702P, and having it to run everything on there. So PC2 and C2. But I have been limiting then my throughput to not the full 3 tips, not the full 2.5 tips, but probably a little bit lower, just to make sure that it can run everything on one box. But if I'm offloading some of the C2 to my miner node, or my miner server, then I would probably get up to the full 2.5 tips a day. So you can start to see here that it's not as clean if you do this. Also, if the market node is running really heavily, it could also impact your sealing performance. So it's like, it is kind of a cheaper setup, but it should still be pretty safe in terms of that your daemon and market node is running separately. So they won't, the volatility from what can happen from incoming deal activity won't have any effect on your ability to prove and to sync the chain. And that's the most important here. But that's basically all I have to say about this part of it, because this is just to say, like, go look at the full 1 pip size setup and say, hey, I can get rid of some of this stuff. I don't need to fill it up with all almost 100 drives to start with. I can just start with something lower, and I just know that it's all set up correctly. So I can basically just swap in the drives and initialize the arrays and attach them to the miner, and now I'm up to the full capacity. And that might make more sense when we move to the next slide here, which is basically just telling what is bill of materials on something like this. So now I'm getting really specific. I cannot say that these prices are like what you can get right now out there, but I tried to Google most of it just to get a reference price on what is, what should be possible to get, just to get a price on this. And you see that if you go with a design like this, which is a 1 pip setup, I would call it probably not enterprise grade, because it is still, it's not even a bare bone. It is still something that I've screwed together, but the hardware components in there is pretty enterprise-ish. Well, the cost will also be pretty significant. So we are up to almost $100,000 for the full setup here. So that's not nothing. But then again, I think what we need to do here, and that's also what I pointed out here in the lower left side, is that basically, if you look at this, $100,000 on the hardware, yes, but you have almost $500,000 on the collateral that would go into these boxes if you're actually sealing only verified deals. So the thing is, like, yeah, hardware is expensive, but on the other hand, it's like you are putting a lot of trust into these systems. And I know that we have both a backup side now, and we have our primary side, and we have these, it's all on rated storage. But it's like, if you lose this data, well, that is potentially $500,000 of collateral that will just be lost, and that would be pretty bad. So it's like, I can see why people would go with something like cheaper and consumer hardware and so on. But if we are on mainnet and we start getting into verified deals and we want to go big, it's like, why on earth would you spend $10,000 on your mining rig, which is holding like a ton of collateral? That's just like, that doesn't really make any sense. It's just too much risk. If you're not running rated drives for your OS, all that kind of stuff, it's like, if things goes bad and you can't really recreate, you can't prove, you might end up with the lost collateral. It's like, that's not really worth it. And I kind of found out this moving from back in the days and calibration net, moving to the mainnet launch and doing space race and so on. I started out with having none of this in control. Like I was just setting up a test system, and now it went into mainnet, and I was like, whoa, we probably need to do something about this, because I'm taking like a risk that I'm probably not really happy with doing. And what I'm trying to do here is more saying like, yeah, it's getting expensive, but then again, you know, if the goal is to put verified deals on there, and you see how much collateral you want to put on there, well, it's you probably can't take those kind of risks on the hardware. So that's it. The hardware cost percentage I put out here, so that's about 70% on this, which be buying physical hardware versus how much you need to on collateral. Another thing to point out here is like this will be using, I won't say burning because it is collateral, but it will be using about, if we use those $20 per fill right now, it would be spending about $3,000 a day if it's sealing at full capacity. So that's basically what you need to feed it with the fill to onboard data. So that's kind of a lot. And another thing in here is like, it will probably take about half a year to fill up the storage. So if you just fill it all up. So obviously you can also do the math on if you only start out with having 24 drives in there, just having this set up 24 drives. How long time would that take, and you know, what is the schedule for when I need to buy new drives so I'm ready to put them in, so they're initiated and ready to go when I'm out of storage on the first arrays. So that's perfectly easy. I've been, you know, starting out with the first 12 drives and then 24 and then gone from there. So yeah, I think it makes totally sense. But then again, you know, with the hardware scarcity and so on, it might make sense to just be on top of it and just make sure that you have all the hardware available. So that was the full 1 pip setup. And then I will move into the other setup here, which is the like a minimum again. We're down to about half the cost, and that was kind of what I was going for, like saying like, yeah, you can also do it cheaper, like $50,000 US. You can totally build stuff here that is $10,000, $20,000 and so on. You just have to think about the risk. Like the more consumer stuff you put in there, probably the more mean times between failure you will have that could cause a breakdown. And what I really want with the miner node and that, like the physical hardware there, is that it's in a setup where it just doesn't break. And obviously consumer grade hardware today is also pretty good, but it's like, if it does break and you have a ton of collateral in there and your miner has no way to prove your data, it's like, that's probably not a place you want to be. So it's like, you can't go cheaper than this, obviously, but it's also a matter of the risk. And we see like if we go down to a system like this and we only have those limited raw capacity because of the 2 arrays, then we would also have a bigger hardware cost percentage. So obviously, yeah, we need to spend more on hardware and we get less amount of adjusted storage power out of it. That's just how it is. And again, on this setup, probably it would take about 2 months and then it's filled up, because the sealing capacity didn't go that much down. So it's like, it's okay. It's just not as nice as having a totally separate sealing setup from the miner. So that's it. As last time, I did bring some pictures just to show what I have been working on. So currently the setup, I'm just gonna move my picture down here, but up here in the left top, this is a look into one of these node servers that I've been building. And basically what I like about these are the Supermicros. Bare bones I like a lot as well, but what I like about these is that you see that instead of having an active CPU fan on there, which could break, all kind of things could happen, it's using a big shroud and it's using a passive cooler, and you have about 4 fans that is actually providing the airflow over the memory perfectly and over the passive CPU fan. And that's really good because, you know, basically this just doesn't break. And if it does break, this is hot pluggable, so I can replace some of these CPU fans, and I have no downtime on the miner. And that's one of my key points here. Is like, obviously I would have downtime if I prune the chain or do Lotus upgrades and so on, but I would really like it not to be, because I have to do hardware maintenance. This just needs to be like rock stable and like never have to touch it. Then next to it you have the Hoesjbo, which is holding all the drives. On this system, it's actually both internal and external port Hoesjbo. So it's like, it is basically holding the 24 drives internally, and then it's also connected to 48 drives externally, because I use these nodes as JBots. Then next to it you have the A4000. I only have one card here on this picture, but that's basically that little GPU sitting there, perfectly doing all the winning post and window post. Then down in the left here we have one of these. This is an HPE server, but it's a good example of what a barebone looks like. And this is basically in the configuration which it would look like if it was used for machine learning. But this looks very much like what we would spec it like for Filecoin. So you have the 32 DIMMs there, you have the CPU coolers, and then you have the GPU sitting there in the back. And basically, because we're using the Quattro RTX A 5000 there, they sit perfectly in a server. And if you're trying to use any of the consumer NVIDIA GPUs in there, no, I just can't recommend it. It's a bad choice of design. You see these per fit, obviously very nice in there. They have power consumption, which means that they don't go past 60-70 degrees Celsius. It's all good. So that's basically what goes down there. Right here, where my picture is, we have what my backup node looks like right now. One funny thing is I couldn't really get a real proper cooling out of it with the T4. So what I had is I have a 3D printed shroud here for it with a normal 60mm fan in front of it. And yeah, if you had, you could probably also tweak it somewhere different and then get a better performance. But one of the issues having a Tesla in here is like, this is really meant for having a GPU specific server which can blow a ton of air at it, because the little T4 there is a passive card. So different ways of doing it, but I find this really efficient, because I can actually hold down to below 60 degrees Celsius like that. And over here at the CPU you also have the shroud there, but I didn't have any more of the passive CPU fan, so I just use this one. But it's good to know that it's basically forced air by the redundant fans. So right about that, this is an example of what it looked like earlier on in a rack. These servers are rack mountable, and obviously they go into data centers, and that's also very important to know that if you have a lab and you set it up there like I did in the very beginning, and you move it to a data center, it's not a good idea to have something which was built in a desktop case or like a open case, and now you have to rebuild everything, because now you actually got into a size where you needed to be in a data center and now nothing fits. Also be aware that data centers might have restrictions on exactly what hardware they would allow in there. Having a super micro server like this is just like, that's the most normal thing. So over in the right side I have some of the more fun stuff, so that's what I've been using here. From the first video I also showed a little bit about using my my floor heating to provide cooling for the server, or put it the other way, my ceiling server is actually heating my house. So that was that's mostly relevant for that little test equipment that I've been running here at home, because it's obviously if you have like a 1 pip raw miner, or like 5 pips of storage powder and collateral, you will probably not have that at home. You might, but at least it's like if you move to the data center, well, what you can have at home, if you're doing something like this and using the water cooling. I only have my test equipment here, which is basically mostly the sealing hardware, and that would also be my other point here. Is like, the more you go into like exploring and sealing and that kind of stuff, the more I find it perfectly fine to do water cooling and exotic everything. Doesn't matter that much. The more you go into the kind of the miner node and all that needs to be online, it's on mainnet, it's real US dollars, the more it needs to look like an enterprise redundant server and not like this kind of stuff. So my lesson from the very beginning was at Space Race, I basically had one big pump that was recirculating all the computer liquids into the system that we see here. I ended up figuring out that I was relying on 2 different pumps at the same time, that they would be online and working, and if they shut off, I don't know exactly what would happen to my hardware, but probably that temperature on the water would just rise like astronomically, and I might start breaking stuff. And so when we went to mainnet, that was kind of a concern that that's a lot of risk to take, that you need X different things to work perfectly, or everything will break. And that's why I think that on that side, where you have like the real fill and so on, better go with some enterprise grade hardware. If we are into sealing, yeah, you could lose your data while sealing, so that would be a little bit annoying. But you could also, if you're doing testing, doing CC and so on, it doesn't really matter if it breaks up and you have to clean up. It's like nothing really bad happened. One last point here that I wanted to point out on this side is, like, you see up there that I have, actually I can move my head up there. So just around here you have those 2 fans sitting right next to the water cooler. So this is a good example of what happens if you try to run with something which is a little bit more consumer oriented. This is not consumer hardware at all. This is a Intel single CPU setup. And what happens is that you have your memory DIMMs, they're sitting right next to the CPU, 16 of them. But because this is made for a desktop computer case, they put it in that direction. Therefore, they're not taking up any of the CPU, the PC Express lanes. So it's like you have all the availability for the cards in there. But when you have the memory sitting like that, you have a really bad airflow. And the problem is, like, I have 1 tip of memory right there. They're sitting right next to each other. Unless I force air down on it like this, I will have the temperatures going past 80 degrees Celsius, and it actually shut down on me because I was like almost burning out my memory. That is really bad. And this is some of the issues that you get into. So that's back to the initial question, like, hey man, why don't you just build this on Threadripper, and you can do Threadripper Pro and it can have 2 tips of memory. That's much easier. Well, think about it. A Threadripper Pro, you probably can't find for now any rack mounting solutions for that. You could take this motherboard or a Threadripper Pro motherboard like this and put it in one of these servers, as I showed right here. But if you have your memory sitting probably like you do right here, you'll have an issue how to cool that stuff, because you're basically relying on turbulence around them to cool them. While if you look down at the left right, you see a setup which is made for like perfect airflow. And this would never have any issues with the airflow in a barebone setup like this. But with something like this, you probably just get into these kind of solutions where it was cheap and you got a very efficient setup and so on. But you end up with something where you have like fans sitting around, and basically, this would have been better just being in a desktop case, and trying to put it in a rack case, that just gets a little bit annoying. So that was just the main point that I wanted to do on the consumer hardware. Then yes, it works perfectly fine if you just want a really simple setup. If you just want to try this out, probably you want to do that on the testnet, not using real film, not using real US dollars on the network. But if you are moving into mainnet, no, minimum will be that you have 10 tips of adjusted power. That's not a lot, I know, but 10 tips of verified power right now, of adjusted storage power, will give you one block reward, like, I don't know, maybe in a year if you're lucky. So it's like you're not going anywhere. So if you go to mainnet, I would guess it's because you want to store real data, it's because you want to mine blocks or something like that. So if that's your ambition to get your hardware cost back again, you do need some kind of size. And if you do need some kind of size, you need to think about that this might end up in a data center like everyone else is doing. You might co-locate to a data center. And if you build this on consumer hardware, which is not really fit to be in a server, probably you wouldn't have your co-locating a site liking that you put like all kind of water-cooled rigs in your rack there. So it's like you need to think about, like, if this is just for fun and this is just to get started and so on, by all means, go ahead, do something. It might not be exactly enterprise hardware, all of it, but think about the long-term goal here. If it is about putting it into a data center at some time, if you succeed, it's a little bit annoying that you have to sell off all this consumer hardware and then have to buy all new because now it needs to be enterprise grade. And believe me, I've been through all of this. So the only thing good I did was to start off by an Epic, so I've been keeping that for the whole time. But most of the other hardware here needed to be replaced. Not spending too much time on it, but the one that I got right over here next to the water cooling, that's actually one of the test machines that I have right now, and it's really like, I don't think you can go server grade more low key than this. It's I kind of ripped apart a 2U chassis. It got the water cooling in there. What you see right there in the side with lights on, that's actually my old 3090 Founders Edition, which is up here in the upper right corner. And yeah, it's water cooled. So it's a very different size from when it had that giant fan on. But right now it's just sitting with a PCI Express riser on there, so it's just lying on the side. So this is like, it's a really, really cheap design. But the reason why I have it sitting like this and looking like this is because I'm only using it to come up with these results that I showed here today. So I really hope that you liked this video and you found it interesting, some of the points that I tried to make here. I know there's a lot of information in here and it might not all make sense, but I hope for some of you it does. If you're very new and it's the first time you ever looked into Filecoin, this is very hardware specific, and I know I said that it's also because I really like it and also because I think it's one place to start with this, but obviously there's also a lot of different places to go to look out information. So what I wanted to point out here on the last slide is, like, if you want to get more into this, you can go to the Slack community channel, which is basically where most of this happens. So this is where you can get help with your setup. This is where you can talk to the rest of the community about how they're doing stuff, how they're setting it up. Obviously there's no single way to doing stuff, but if you have an issue, this can be a really good place to go. There's also a GitHub site there. Both GitHub in itself for the Filecoin project is really good, with a lot of content in there, a lot of issue tracking and everything going on in there, and also the new releases will be in there. But also this specific site also hosts some links and everything to the different community sites, also Slack being one of them. Then I would like to point out that we have Hoesjbo, which is an enterprise storage provider accelerator that Picnic is doing. So that's the company where I'm working, and I'll also be one of the instructors at that course. It will go on for the first cohort here in Las Vegas in a couple of weeks, and basically will keep on going. So enterprise storage, that is obviously for bigger storage providers, So I would say, looking at who is attending, I think we're talking like 10 pips and up to exabyte scale. So obviously the video here and what we're doing here is like, that's just to kind of get the basics of what is actually the mechanics of the Filecoin storage provider process here, and not what you do an exabyte size. But if you have interest in that, the link is there, and it's an accelerator which will take on 50 participants for now, brought in different cohorts, so it's like open for application for the next cohorts. But I would also like to point out that there will be other accelerators coming up. You could call it like operator training programs. And right now, ESPA is running in North America, Europe, Asia. There will also be a lot of this training. Also, the ESPA training material will be come out in the public. So it will basically be available both for these other training courses, but it will also be available directly if you just want to get to know more. But I hope that this was kind of a teaser on what you're up for if you want to do real data and you want to do Filecoin. If you are a storage provider out there, I hope that this gave you some inspiration on, what you could change and what you could look out for to optimize your current setup. And that was basically all for this one. Let's see if there will be another round once hardware seeding speeds and everything is updated again and we have something else for the market and so on. I am enjoying myself very much on this network. I think it's one of the most promising blockchain technologies. I really love the fact that what we are primarily doing here is providing storage, and we actually have that consensus mechanism and everything coming on top of it, meaning that in the future we're doing data, we're doing storage. I'm very much looking forward to getting the Filecoin virtual machine, so the extended kind of smart contracts on there. And I would really love to see when we can start doing also distributed compute and stuff like that on the data that we are storing. Basically, I think that we're just getting started. We're just getting where, basic things are working now. We can store, we can retrieve, and that's starting to really look good. But think about it when we move into actually also doing like extensive smart contracts, being able to control how we are storing our data from a client perspective, being able to compute on those data. We have all this hardware already. We have tons of GPUs and everything. So why not also being able to do that? So it's really an awesome future that we're looking into. And I think that the more we get into it, the more we will see that that this is really the next World Wide Web that we are creating right here. Awesome, that's all for me this time. Have a good one, everyone.